So in this video, we're going to do a more formal summary of what we did with the college applications or school applications data. So it's going to be a look at measuring variability for one variable data, and it's certainly going to be quantitative numeric data. So here's the objectives for the video. We want to be able to find the range of a distribution of quantitative data. So range is something you are probably familiar with from middle school. So we're just making it sound a little fancier by saying quantitative data there. We should be able to find and interpret the interquartile range. Now, that's a topic that might have been addressed somewhere in your previous schooling, but it's not so bad even if you haven't. And then finally, we're going to calculate and interpret the standard deviation. Now, that is probably a brand new topic. It comes with notation, it comes with interpretation. So we will actually carry this over into the next class. But let's talk about variability. So being able to describe the shape and center of a distribution is a really nice start. But two distributions can have the same shape and center and look very different. So this is our first set of bowling scores. They're bowled by Earl. And just a quick question, if we had to use a word to describe the distribution, would we call it skew? Would we call it symmetric? Would we call it uniform? I'm thinking of using those hedging words. I'd say it's approximately symmetric. There's that kind of single peak in the middle and it falls off in both directions. Admittedly, this side looks different than this side, but I think that the number of scores that fall on this end and the number of scores that fall on that end, pretty similar. So I'd say probably approximately symmetric. And then how about an approximate value for the center of Earl's bowling scores? And not only is there a big stack there shortly after 150, but it also feels like there's probably an equal number of items to the left and to the right. I think if we average them, this would kind of these would weigh these out. So I'm feeling like a little bit over 150 is probably a good guess for the center of the distribution. Now here's a very different bowler. This is Kelly. And I say very different, but maybe it's not so different. To me, it looks different because there's such a tighter bunching there. But if we were to go through those same two questions, what's the shape of the distribution? Probably, again, go with relatively symmetric. Now, it's a different kind of symmetric than Earl's, but it's still peaked in the middle. Left and right are balanced out. I'm not saying that these two look alike, but at least their shape, I would still use the word relatively symmetric. And how about if we went with an average? Now, you could probably argue that this outweighs this a little bit, but these over here are going to start pulling the average. So I think, once again, that average is probably very close to 150. So I think both distributions are symmetric and single peaked. Their centers are around 150. But there's that issue of kind of spread, let's say, and kind of the fact that Earl is all over the place with his bowling scores and Kelly's very, very consistent, that we would like to be able to describe somehow. So that's variability. So some of the common ways that we're going to measure variability are range, interquartile range, and standard deviation. And as I said before, range is probably something you're pretty familiar with. That's just kind of how far a spread is there from the beginning to the end. Interquartile range, we have to talk about quartiles first. You'll find it's not so bad. And then standard deviation is really the focus of today's lesson. So the range, it's just the distance between the minimum and the maximum value, as I said. So it's a simple subtraction. And if we went back to those bowling scores, you wouldn't say the range is from 100 to 270 or something like that. You would give me the answer to the subtraction problem. So you would actually take the 100 minus 270, or 270 minus 100 more correctly, and say 170 is my range. But it's just by taking the max minus the min. Now, the thing here is this, it's not a resistant measure of variability, it says. What they mean by that is, if you have a high value or a very, very low value, some sort of outlier, that range is going to feel the impact of it, because after all, the range uses the highest and lowest as a part of the calculation. So if you had one that was way out of the norm and was an outlier, that's going to impact your range. So it's variability, but it's not a resistant measure of variability. So let's start talking about how you can describe variability maybe in a way that would protect against an outlier. So we can avoid the impact of extreme values on our measure of variability by trying to look at maybe just the middle of the distribution. And we can't talk about the middle 1 point because that's not really a variation at all. You'll see what we mean when we say the middle. So if you order the values from the smallest to largest, and this is some collections, I guess, that went on by somebody. And if we order them from the smallest to largest, I just took the dots that I see here and I labeled a number on them. So here's your 39. And if you order them from smallest to largest, we can find the middle, the way they're describing the middle, by finding quartiles. So as it kind of suggests with the word quartile, there's going to be 4 pieces. And when you have those 4 pieces, they're going to have an equal number of items in them. So you've got a little familiarity. You've found a median before in your life in the last class, actually. So the median actually is finding one of the quartiles. It's the second quartile, because your first quarter and your second quarter have happened by the time you get to the middle. The first quartile, as I already mentioned, is kind of in that first half of the data. So what you do is you find the midpoint of the first half, and that's called the first quartile. We call it Q1. And then similarly, we do the middle of the second half. Now, you can notice that these values are spread out over a longer distance on the number line than these are. So when we're saying break it up into 4 equal pieces, we're talking about the fact that there's 3 items in each of these sections, each of these quartiles. So the quartiles is about how many items are on the list, find the middle of the first half and the second half, and you've got your quartiles. So if you've got the quartiles, and this is just a summary of that, now you're well on your way to finding the interquartile range. So if range is the distance from the highest to the lowest overall, interquartile range is the distance from the first quartile to the third quartile. So it's that middle section of the graph. It's the 2 pieces, those 2 quarters that make up the middle. So that's Q3 minus Q1. And the quartiles and the interquartile range are resistant because they're not affected by a few extreme values. If you had like think about the schools that we did today. If you had a group where the highest had been 40, and then all of a sudden another group of applicants end up having 70 applications, you replace the 40 with the 70, it hasn't changed your median and it hasn't changed your quartiles either. So they're going to be much more resistant to an extreme value than overall ranges. And then the last piece here is standard deviation. And like I said, this is probably going to take a couple of days, but you did a lot of work with it today. It's just that now we have to kind of formalize it. So if you summarize the center of a distribution using a mean rather than the median, you've kind of stopped heading down that path of median, quartiles, interquartile range. So if instead you're going with the mean, we're going to use this thing called the standard deviation to describe the variation. And the standard deviation, it's a logical measure, I think. It measures the typical distance of the values in a distribution from the mean. So there's a mean for a set of data. Think about the pictures of dogs possibly that I opened class with. And we could say, well, typically the dogs in this photo are pretty close to the average. Or you could say, yeah, there's an average mean, but typically you're either going to have much, much heavier dog than that or much, much smaller dog than that. There would be a bigger standard deviation because, again, the standard deviation measures the typical distance of the values in a distribution from the mean. To find the standard deviation, we follow a lot of steps. First of all, you need the mean. Next, you need to find out how far away each item is from the mean. So you can do the value on your list minus the mean. You'll get positive ones for over average items, and you'll get negative values for under average. Before we start adding them up to kind of compile them, we want to take that positivity and negativity out. So we'll square each. We'll divide by that grand total by n minus 1. It's sort of averaging, but there's a greater purpose for the averaging. That is the reason we do n minus 1 instead of n, like the number of items. Strangely enough, if there were 9 sets of school scores, school application numbers, we wouldn't divide by 9 after step 3, we would divide by 8. And then you take the square root at the end so you can kind of unsquare it and take it down a notch from this inflated value we got from squaring. So the formula for all that is this guy here. And luckily, we don't often use formulas in this class. So we don't often write a ton of our work out. Instead, we'll just have to know what technology can help us do that. And more importantly, we're interested about the interpretation. So a couple items about standard deviation. If it's going to be the typical distance from the center, from the mean, for an item on the list, it would make sense that it's always going to be greater than or equal to 0, because distances, we like to say, are always positive. It does say that the standard deviation could be 0, which is pretty weird, but that's only if every single value was the same number. So they would have an average, and every single one would be right on the average, and so on and so on. Larger values for the standard deviation, and this is the notation for that, indicate greater variation. So if you think about the bowling scores, where we had Earl, which was the first set that we saw, and then we had Kelly, which was the second set, the one with the greater variation was the one that was spread out all over the place. So we would, if we took all their scores and threw them into Staplet, we would find out that Earl had a greater standard deviation, because typically his score was a little bit further away from his average than Kelly's would have been from hers. The standard deviation is not resistant. If we had a wildly high or a wildly low score, you better believe that that's going to impact your description of how far away from the average items are. If you've got one that's way further away from the average than the others, it's going to increase. So it's not resistant. And then finally, it measures variation about the mean. It should only be used when the mean is chosen. So if you're talking about medians, you're down that path where you go quartiles and interquartile range. But there is, it's not like you get total choice for which one you're going to use, because when you think about the mean to begin with, that is affected by extreme values. So if you wanted to be fair about the way you're describing the center, if you had a really extreme value, if you had potential outliers, you probably would have gone with the median as the center. So that would have led you to IQR as the variability. But if you're looking at a relatively symmetric graph, like you were with two of the bowling scores, then you could probably go with the mean as the average, and then the standard deviation is a nice complement to that to tell you how it varies around it. So hopefully at this point, we've got the range of a distribution. It's just highest minus lowest. We've got the interquartile range. Takes a little bit of work, very similar to your median work. And then calculate and interpret the standard deviation. Still may be a work in progress. It starts by finding the mean, and honestly starts by taking the data and getting into a stapler or a calculator to do a lot of the heavy lifting for you.